Hello, this video is for Stat 310, Handout 8 Part C, and it's going to cover pages 18 through 25. Okay, let's go ahead and get started. So Handout 8 Part A, what we did there was the overall one-way ANOVA test. Handout 8 Part B is where we did our multiple comparisons. And here in Handout 8 Part C, we just have some additional things like checking the assumptions and also looking at power. So here again is the setup. It's a sleep deprivation, our data. On page 19 here, we have the outcomes from the Part A, which was the overall test. We have the individual effects or the main effects here. In Part B, we were looking at the multiple comparisons. Like I said, we learned that 30 hours was different than 12 and 30 hours was different than 18, but no other pairwise comparisons were different from one another. So how about some additional outcomes? So we'll start here with the residual versus predicted plot. Now this is given to us when we look at our fit model output. So let me go over into Jump and just show you where that's at quick. Select Analyze, Fit Model. Number of touches is my response. Sleep deprivation level goes down here in the effects box. Click Run, and we will obtain our standard fit model output here. The residual by predicted plot is the second plot down here. It's this one here. So what kind of features do we want in this plot? So let's go back to the notes and talk about that. What this plot is doing is checking it's ensuring that the model that we're using is adequate. We don't want any unusual patterns in this plot. If we saw something like a parabola shape, that would be bad. Or if we saw outliers. So here my observations or my residuals here, or my errors here, that's on the y-axis, go from about -4 to 4. If I had an observation way up here at 10 or something, that would be a problem. That would be an outlier. So we want to pay attention to whether or not I have outliers in the vertical direction here, either way high or way low. We also want just kind of uniform scatter. We want the tops to be fairly close to one another and the bottom here. If I ran into a situation where on this side I didn't have very much variability, so let's suppose that the spread over on the left side was not very much at all, but the spread over here on the right side was a lot. That would be a problem. Call this kind of a funnel pattern here, or a megaphone pattern. Or it could be switched around. If we have that problem, then the constant variance assumption is probably being violated. Now, we can do a formal test. We had these earlier in the semester where we did a formal test to determine whether or not the variances were the same or not. Now, to get this output, I need to go under fit y by x. I cannot get this output under the fit model. So I'll show you that quick here. I need to go under Analyze, Fit Y by X. Number of touches is my response. Sleep deprivation is my X factor level here. Say OK. And then from my drop down here, I'm going to select unequal variances. So this is the same as what we did when we were doing t-tests. But here I have 4 different levels here. So these equal variance tests will be done across all 4 of those levels. Here is the p-values for those tests. None of those are less than 0.05. I said before that these tests are not real good. They're kind of finicky. And Jump actually gives us 4 different tests here. The O'Brien, Brown-Forsyth, Levine, and Bartlett's. In this particular case, all of those tests indicate that my equivariance is not a problem. If these p-values were less than 0.05, then I would have problems with the equivariance test. But because they're not, my equivariance assumption is okay here. To be honest, most of the time we just verify that assumption informally by looking at this plot. Okay, how about some of the other things? Here we have the normal quantile plot of the residuals. I can get this underneath the fit model output. So now I'm going back underneath fit model, and from my red drop-down menu, I'm going to select row diagnostics and then plot residual by normal quantiles. Show you that real quickly here. Let's get rid of that. Go back to my fit model here. Row diagnostics, plot residuals by normal quantiles. And that plot's going to be dumped out here in the bottom. What we want in this plot is the dots to fall in between these bands, which they do. So my normality assumption is okay. So the assumptions for one-way ANOVA are just like a t-test. Should have equal variances, observations should be normally distributed, and then I need independence as well. And the people that are in the sleep deprivation 12 group aren't going to influence any of the other groups. So these groups are independent of one another, so I have the independence assumption. There's not a formal test for the independence assumption. You just need to think about how the experiment or study was done to verify that assumption. All right, a couple of other things here. I'm just going to go over and jump and show you these. One's the factor profiler, and the other is the least square means plot. So let me go back over into jump and show you where those things are obtained. From my drop down here, I can select factor profiling and then profiler. And this is just an interactive plot that allows you to specify different levels here. Let me just kind of bring that up to the center of the screen for you. So I have a vertical line here, both in the horizontal and vertical direction, a dotted line, excuse me. So if I wanted to know what would be happening if I had sleep deprivation 30, I would just take that vertical line and slide it over to 30 here. This is going to give me the estimated number of touches on average for that group, 6.25, and here's the confidence interval for that. These are the same confidence intervals that we obtained when we were looking at handout, or part A, excuse me. I can specify different levels here by just moving, again, these vertical lines around. That's the factor profiler, or what they call prediction profiler. The other thing that I can get here up in the upper right-hand corner is an LS means plot. So again, this is not the red drop-down menu. We got two red drop-down menus here. This is the one over by the factor level here. The factor level is being specified here. Just go ahead and minimize those things. I can ask for the LS mean plot here from my drop-down menu. What that's going to do is give me something real similar to what we were just looking at, except it's not interactive. So here's the 12, 18, 24, 30. And here are the confidence intervals for the average number of touches. The other thing that I want to talk about quickly is the power analysis here. Okay, that power analysis, just like we did with a t-test, we can do this in one-way ANOVA. So let me go back to the handout here, look at page 23, talk about the power. So again, from the red drop-down menu, select power analysis. My first window that I'm going to get looks like this one on the right. I'm going to be using, so this is all automatically filled in here. So the alpha level is 0.05. We're going to keep that the same. That's our standard alpha level. The 1.476 is the root mean square error value. That's just the average residual value. Again, we get that from our jump output. Right here, my root mean square error value. This thing is just the square root, okay, of my mean square error. So we talked a lot about that in handout 7, I think it was. So the square root of that is just this 1.475 here. So again, this here, the root mean square error, is just the average residual value. And that's needed here when we do our power calculations. The effect size is denoted by the delta here. That defaults to 1.23 there, which is probably the average difference across all the comparisons. It's probably the default value there. The number is just my total sample size. I had, I think, 8 in each group. I had 4 groups, so that's 32 there. So if I leave this kind of as the default and say solve for power, click done, it's going to do a power calculation for me. This power here is a probability value that is between 0 and 1. It's very high to 1. It's close to 1. That means I have a very high probability of being able to detect a difference of at least 1.23 across my treatment level comparisons. And we were able to detect two different ones. Again, they were 12 to 30 and 18 against 30. Now the next power calculation is, suppose my effect size is 1. So I left alpha and sigma the same, but my effect size is 1 here. So what that means is I want to be able to detect at least one additional touch. That's what effect size means here. I'm going to vary my sample size from 12, which would be 3 in each group, up to 48, which would be 12 in each group. I have 4 groups here, so 12 times 4 is 48. I'm going to solve for power again, and I end up getting a power curve or a power plot. I got to select the red drop down to get the plot. So how do I use this? We usually, in our analyses, want to go after about 80% power. So I'm going to snap a line here at 80% power. I'm going to hit my power curve and drop down, and we can see that it's about 30 or so. I said 28 here because I had 4 groups. 28 divided by 4 is 7. So I need at least 7 per group. If I want to achieve 80% power, I need to put at least 7 in each group. And that again was to be able to detect an effect size of 1. If I move all the way up to 12 per group, which is going to be way up here at the top at 48, I'm almost certainly going to be able to detect the difference, if it exists, of 1 or anything greater than 1. However, if I bring my number of replicates down to 12, okay, I don't have a very good power anymore. My ability to detect is not very good. So I'm not going to be able to detect at least 1 additional touch with only 3 replicates in each group. We had, I guess it was 8 replicates in each group. Okay, so I'm going to be above that 80% power. All right, that does it for handout number 8, part C. Thank you very much. Have a good night.